thank you to organizers for the invitation and this opportunity to give a talk. So I'd like to tell you about homological representations of surface mapping class groups. This is joint work with Anna Belikova and Christian Blanchet. So I'll be interested in closed-oriented surfaces with one boundary component. I'll denote it by sigma G1. G indicates that the genus is G, and this is just one boundary component. And then I consider the mapping class group of this surface relative to the boundary, which means that just consider classes which fix the boundary of the surface. And then we want to construct some faithful representations, ideally linear representations, but the first step would be to find some nice faithful representations. And the approach that we use is to consider homological representation. And you might think that that the homological representation is something like we take homology of this sigma and consider the action of the mapping class group, but you know that this is not faithful at all. It has a huge kernel. But then a more interesting representation looks like this. We take the homology groups of configuration space of this surface. So this is unordered configuration space. This is the set of n unordered points in my surface. And then this representation is better, but also it is known that for each n there is a non-trivial kernel of this representation. Although it is asymptotically faithful. So if we take the limit of n to infinity, then it is faithful. But then the picture somehow can change if we slightly modify it by adding some local system here. And I want to argue first and give some motivation why this construction is actually good. And the first instance of this construction is the theorem about linearity of braid groups. So it was proven by Bigelow and Kramer independently, and the proof is essentially about this object. We take the second homology group of a punctured disk. Yeah, so for now, the object here will be not a surface but a punctured disk. And then we need to take some special local system. I will tell what is it exactly a bit later. So there is an action of mapping class group of this disk on these homology groups. Let me denote it by dn. So the action from the action on the configuration space actually can be extended to the action on the covariance space. And the main result is that, of Bigelow and Kramer, that this representation is faithful. And then you can make a linear representation out of it by sending this local system to R. So you can just embed this ring into R by sending T and Q to some algebraically independent values. So this is one example. Then quite similar construction. So using this homologies of configuration spaces, there is a way to describe John's polynomial. So this is a topological way to define it. I will not go into details, but the idea is that you represent your knot by some braid as a closure of some braid. Then this braid is an element of this mapping class group of a punctured disk. And then John's polynomial can be obtained by as an intersection number between two embedded surfaces. So this is intersection in homology of, again, some configuration space of a punctured disk in some local system. So there is some way to embed a sphere and a torus into configuration space. Then you act on the torus by this braid element or mapping class group element, and the intersection is the John's polynomial. So these representations know something about quantum invariance, and even more, there is a recent result of Marco De Renzi and Jules Martel that, well, I think I will not give a rigorous formulation, but I'll say that if we take sum of all homology groups, there is some slight modification of configuration spaces, and in this case, it will be at configuration spaces of a surface, relative to some subspace and with some local system, which I will describe a bit later. Then this is also a representation of a mapping class group of this surface, and in some sense it reproduces some quantum representations which come from non-semi-simple TQFTs. So the theorem says that you can, so you have some quantum parameter here, you can specialize it to some root of unity, and then there is finite dimensional sub-representation which coincides with the representation of mapping class group which comes from some TQFT. So now I would like to, what I want to tell you is a generalization of this fact. So we want to extend this idea to surfaces here instead of disks. And for that, first of all, I will recall a little bit how this representation works and why it is faithful. But instead of this particular homology group, I will talk about slight modification of it because it's easier to work with Bahrain-Muru homologies in this case, because the configuration space is not compact, and it will be more useful for the generalization. So consider this space. So this is just the configuration space of punctured disk. But now I consider it relative to some subspace, which is just a subspace of points in this disk, such that at least one of them belongs to the minus boundary. So this minus boundary means that I just take my punctured disk and I split the boundary into minus and plus component. And then let me say what is this local system. So I think about a local system as well, let's say it as a homomorphism from the group ring of configuration of pi1 of the configuration space. To this ring. So you can think about loops in this configuration space as braids, and then following these 2 points, you can define 2 integer parameters of a braid. One of them is the Winden number of this braid around each of the punctured points. So I have, let's say I choose some base point on the boundary, and then I follow both points. They convene somehow around the punctured points, and then I send this loop to q to the power. So this will be the sum over all punctured points of the Winden number around these punctured points of both components. And the second parameter, this is just the Winden of these points around each other. So for example, this braid, which just switches these 2 points, will be sent to t to the power 1. So this is the local system, and the reason why this representation is faithful is because you can look at the pairing between. Let me write here sigma, because it will also work the same for surfaces. So I have some local system here. You can take the usual homology. But relative to D plus. Using this pairing, I can associate to a pair of curves on my disk some element of this local system in the following way. So I have my disk So I have some curve relative to the minus boundary, and curve relative to the plus boundary. So this will be a bit asymmetric, but what I do, I take a copy of this curve just parallel to this one and close enough. And then I can associate two homology classes to these curves. So for the blue one, I can take see, this is zeta minus. This is zeta plus, and the copy that I draw is zeta plus prime. So for the first class, I take the configuration space of 2 points on zeta minus. It will be a class in Borel-Moore homology relative to the boundary. And here I just take the class, the fundamental class of the product of zeta and zeta prime. And then this pairing says something about intersection of these curves. Actually, the key lemma in the proof of faithfulness of this representation is that this algebraic intersection detects the geometric intersection in the sense that if so the algebraic intersection is trivial if and only if there is an isotopy of one of these curves, such that you can eliminate all the intersection points. So, for example, if you have these two curves, this is a non-trivial geometric intersection because you can't eliminate these 2 points. You can only add new intersection points. But if I draw something like this, then I can apply isotopy, for example, to the blue curve, and then this is equivalent to this picture, for example, where these curves don't intersect. And now, so it means that you can choose a set of curves. Yeah, let me draw it. So I have my disk. I choose a set of curves relative to minus boundary, a set of curves relative to the plus boundary, and then I act by an element of the mapping class group only on one set of these curves. And if the intersection has changed, then the mapping class is not trivial. And I know that the geometric intersection is detected by the algebraic, so it means that I can detect any non-trivial mapping class by this intersection, or what is equivalent by the action of this mapping class group on mapping class on this representation. Okay. So now I can do the same. So I already wrote here sigma, which means that I will consider not a disk but genus G surface. And a good picture here is that we had a disk, we had some punched points, and now we glue genus 1 subsurfaces instead of these punched points. In particular, it means that there is an embedding up to some choice of the mapping class group of a disk into the mapping class group of the surface. So it gives a hint what we should do, how we should modify our local system or our representation in order to get something faithful. We need at least to do something that is restricted to this disk, is of the same form. And so that's what we were trying to do. In particular, we want to find such a local system that this representation is faithful, or which is more or less equivalent, that the algebraic intersection detects the geometric intersection. And well, first of all, first claim is that this local system can't be abelian. Because it means that we must look at a homomorphism from the surface braid group to some abelian group, and restricted to the disk, it kills all possible parameters. So maybe so in the surface braid group, which is just by one of the configuration space. I have some. I have a canonical element, which I will call sigma. This is the braiding element. So this is exactly the braid that just switches to points. And if you require the local system to be abelian, it automatically means that so that automatically means that sigma square is equal to 1. But then, if you restrict to the disk and consider these loops, so we know that in the case of the punctured disk, we need to get something that counts the winding number around these punctured points. But if we take the abelianization, actually this loop will be sent just to 0 because it bounds some subsurface, so it's homologically trivial. So at least one of parameters doesn't survive, and there is another parameter which was exactly the braiding, and its square is equal to 1. So this definitely doesn't work. Then the next idea was to take the first non-trivial non-commutative local system, which is Heisenberg group. So we take the central extension of the first homology group of our surface, and this extension is given by the intersection number, and it turns out that you can think about this group as a quotient of the surface braid group by this canonical by this commutator with the canonical generator. So in this case, sigma square is not necessarily 1, so we have the whole center corresponding to all powers of sigma, and previously I think people thought that this might be a faithful representation with this local system where we put here the Heisenberg group, but it turns out that this parameter is still not visible in this case, so we need even further extension. Yeah, and maybe running out of time, so I can just say that we have this construction that if we take first the pure braid group, then there is a way to construct a local system for this group by taking some bigger extension of homology groups. And then, since this is an index 2 subgroup of the braid group, we can induce a representation, or we can induce a local system on the whole braid group. And so maybe we call it H prime, and then we have so we have this local system, and maybe just 1 minute. The last claim, which is work in progress, so I need to check some details. Let me just write it here. That if I put this new local system here, it's better to write the group ring. Then this is a faithful representation of the mapping class group. Okay, that's all. Sorry for being over time. So we need it to be non-abelian because we want this braiding parameter to be some free parameter in this local system. Because when we reduce to the disk, this must be a free parameter in the Lorentz-Kramer representation. Yeah. Well, okay, I think I'm not sure that it's not faithful, but most probably it's not faithful because it doesn't recover the Lorentz-Kramer representation on the disk. Sorry, I can't hear. Yeah, I can't give a particular element in the kernel. So I'm not sure.